We're going to see the intuition of the wave equation. This is just the mathematical equation, it's not the most beautiful equation in physics of the wave equation that has the second partial derivatives. Here we're just seeing the graph of y of x and t is equal to a cosine of, you can say, kx minus omega t, or some variants that we're going to see. First, let's say how could we develop, or how would we explain this shape of wave? Because this is the representation of a transverse wave, but it's also the graphical representation of a longitudinal wave, in the sense that here we are having, you could see that more density, less density, and so remember that the longitudinal waves are also called compression waves. Alright, so this, first, how would we categorize this? Look that the maximum is occurring at t equals 0. So this is cosine and not sine. So it would be cosine. Y equals to something cosine of, for now I will put cosine, cosine x, and we will be forming the equation. Here it could be 1, but also could be 3, for example, or 4, or whatever it be. So here I have a cosine x. Remember that a is the amplitude. So I have a cosine x. Now, why I have cosine of kx and not just k, and not just x? This is because, look here, that this has the same as this. Let me say that this is 1 meter, 2 meters, 3 meters, 4 meters, 5 meters, 6 meters, 7, 8, 9, etc. So look that this at t equals 0 is the same as t equals 4. At t equals 2 is the same as t equals 6, etc. So with this, y equals a cosine of x, we have just this equation, or this graphical representation, but I could have the same stuff like a cosine of x, but what happens if I compress this, and so I have something like something like this. So I compress this, so it would be a cosine of, here I would have a larger number. Like, if I compress this, that means that here I have cosine of, for example, 2x or 3x. If I expanded it, it would be a cosine of half of x, something like that. So how would we know what number do we have here? Remember that k is 2 pi over lambda. This is important because if here we put a cosine, instead of x, I put a cosine of 2 pi divided by lambda. This means that when x is a wavelength, is lambda, then I have a cosine of 2 pi. So I have the same as one wavelength previous. So that is, I have here and here. So this one, when I have a wavelength, so 4 meters. So here I will put 4 meters. So I would have the same as, so here I have 0, so it is 2 pi, sorry, here at time equals 0, I have this y equals 3. At 4, I have the same, y equals 3. That means that on every wavelength we will have the same. So if I put here 4, I will have pi over 2x. I will have cosine of pi over 2x. So here I just have a cosine of you could put it as a cosine of 0 here because I have advanced no distance. So here I have a cosine of 0. So a cosine of 0 is just a times cosine of 0 is 1. So I just have a. A in this case is 3, the amplitude. When I advance a wavelength, so here I have a wavelength that is 4. That is when now x. Sorry, I think that I mixed it up. Here I'm putting 4 on x. So when I have 4 here, lambda is a constant value. Lambda is, in this case, is 4. Lambda is a constant value. So I'm saying that when I advance one wavelength, so here I will put 4, then I will have again cosine of 2 pi, that this would be 1. Previously I have cosine of 0, now I have cosine of 2 pi, and it's 1. Now if I put 8, I have advanced 2 wavelengths, so I put here 8. Then I put here 8, so I will have a cosine of 4 pi, and it is again 1, so I have again used the amplitude. So for that, we don't have just y equals a cosine x, we have y equals a cosine of kx, when k is 2 pi divided by 2p divided by lambda, the wavelength. Next thing that we need to take into consideration to construct our wave equation. That is, if I move this to the right one wavelength, that is, I move it completely one wavelength, you will see that the shape is completely the same, but I shifted it. So remember, when we shift something, I have a cosine of, in this case will be, we know that it's 2 pi divided by lambda x minus, if I put a negative and here something, I'm shifting it to the right. If I put a minus something here, so minus the negative of something, I'm shifting it to the left. So the important issue here is that if I shifted it, here I'm graphing it with time. So here I have time. So the issue is that if I shifted it, the time that it takes to complete a wavelength, that is from a period, we would have exactly the same shape. So if I put here minus 2 pi divided by the period times t, this would make sense, because here remember that omega is 2 pi times f, but remember that the period is how much it takes to complete a round. The frequency is how many rounds or cycles occurs per 1 second. The period is how long it takes one cycle to occur, so it's 1 over f. So I can substitute this f from t, and so I will have this. Now this is intuitively correct, because if I shifted it one period, that is when t is the time that it take for do a complete round, I would have exactly the same shape. That is, if here I have you can know that I'm not shifting anything, but if I shift it, let's say to the period, so interval of the period, so here I would have t, and then this would cancel, and I would just have this minus 2 pi. Or I could shift it to times period, etc. So this is in order to shift it, but that the shifted piece be the same as, that is that when we're shifting we are encountering the same. So if I shift this here, it would be the same as if it were here, etc. And lastly, but I'm not going to put it, we can shift it, because this is the exact match, the exact shift. When we're shifting, for example, this I shifted it and it's now here. The one that is here is completely here. But let me put minus, for example, minus 5. This is indicates that I shifted, but out of phase. That is, if now, for example, I have something like look that here it is neither sine nor cosine. I don't know if it looks a little bit like sine, but it is not. Here now you can see that it is not sine. Sine would be here. So this is neither sine nor cosine, so for that we add this phi. So this is the equation of the wave. Actually, if you want, you can just leave it like this. This is the representation